In this video tutorial that corresponds to the chapter 7, we will take advantage of the layout for the game of Breakout that we created earlier in the chapters of this book. This implementation will start already with the config.json file and a script called processing RL metadata that we'll simply call the RL processor in order to create a template specifically designed for AI. I'm going to start by opening this folder and then we can code along. Processing RL metadata takes 2 lines of code. You could run it using an interactive interpreter if you so wish to do. And what it does is calling the RL processor module, which contains a method called map.json. I'm going to run it right now. And at this point, I make sure that my environment is active. And actually, I need to activate it because it's not. It is Pygame_emp, and then I can run it again. Once the program finishes running, we will find 2 new files called RL output and the model. The model is the synthetic brain of our AI, as we have previously discussed, and it contains multiple layers. We may need to modify these ones. RL output contains all of the information that turns our layout, the one we made in the designer, directly into a Pygame game. So we can run it directly and get a layout back, something that we can modify. In this simple implementation of DQ learning, we will use the distance of the ball relative to the paddle. We will normalize the position of the paddle relative to the ball. If the ball is to the left of the paddle, the value will be negative, ranging from values from -1 to 0, where 0 is the center of the paddle, where the ball is right above it. And the same happens if the ball is to the right of the paddle. At this stage, the blocks will have a reward attached to them. It means that whenever the ball hits the blocks, we're gonna yield a reward for the agent. And also, and this is specifically important for this simple implementation of DQ learning, the ball hitting the paddle will yield a higher reward. The penalty of losing the game will depend on the distance at which the ball was relative to the paddle. The longer the distance, the higher the penalty. The closer the distance of the ball at the moment of losing the game, the smaller the penalty, with a minimum of 10. That means that regardless of how far or close the ball ended up at the moment of game over, the minimum value will be 10. So let's go directly to the play step. And in here, we can see that we received the reward and the score, which we set to 0. And in the call to this method, we have only the action, the parameter we are receiving, that is represented, again, remember, as a tuple, or better say an iterator. In this case, I believe it's a list with 3 integers. This is a one-hot vector, which means that this position will only carry one single number 1. If the position of the number 1 is in index 1, the second element in this list, that means nothing. The agent should not move to the left or to the right. It just stays where it is. And as you can imagine, putting it on the left means moving the agent to the left and to the right otherwise. So let's encode this information, and we can start by asking if the action is going to be equal to 100. And if that is the case, we also need to evaluate if the agent moving to the left is touching the boundaries of the left side of the screen. For this, we're going to ask, using a logical operator, if the position of the left edge of the rectangle or hitbox that represents or contains our paddle is touching that left edge. And we're going to take in consideration the speed that the paddle is going to have. So here we're going to take the position left because we're moving towards that direction. And we are going to subtract a parameter called the speed and add the relational expression, which will ask if the value is less than 0. This is basically asking if the left edge of the paddle, considered after the velocity is added to it, is going to touch the left edge of the screen, or is better say it's going to go beyond the left edge of the screen. And actually, we should ask if it is bigger than, not less than, because that is the case where we are still allowed to move left. So we're going to add the velocity to x to this paddle. The same happens in the second scenario. We're going to use an elif statement for it, just because these are mutually exclusive scenarios, although they don't include all of the different cases, in which we are using the movement to the right. And in this case, we're going to add a plus, and we're going to ask if the value is less than the right edge of the screen. At this point, we don't have a parameter called speed, so we need to add it. And we're going to add it at the top of the document. Here, let's set the speed at 5. We can always come back and change it later. Now that we have these parameters, the paddle should start moving at random intervals. Notice here as well that we are not addressing the third case, which is the nothing happening. The paddle doesn't move, and that is for simplicity. Let's run this program again. Let's see if the agent begins its movement. The movement, of course, is being processed through the synthetic brain of the agent, but nothing special is going on, given that the agent doesn't have an understanding of its environment yet. So we are going to add another parameter here that is very important. Notice that one of the internal states of the paddle, and really any agent that we make, is whether or not it's still alive or not. And that is a parameter that we're going to pass from the outside, and it's going to be called isDead. So here we are simply going to set isDead equal to the parameter that we receive when we call the function playStep. At this stage, I am gonna modify the reward to be equal to the reward that we will also gonna receive here at the top. We receive reward, we receive isDead, and let's add a condition as well. I'm gonna comment the score for a minute. In addition to the reward and whether or not the agent is dead, we're gonna also add a penalty, and that penalty is gonna get added to the reward. Now that we have this, or actually I guess I shouldn't comment this out, then we have the playStep method. So let's work on the helper functions. Let's work on the interactions of the ball with the blocks. Notice that the interaction of the ball with the blocks has nothing to do with the playStep, actually has nothing to do with the agent itself. Okay, so let's go to the game manager. So the game manager right now contains a helper function in here, and the reset, I'm gonna move it to the bottom because at this point it's really agnostic. It's not gonna change anything, but it may be a good way to think about the process. So if the agent is actually, yeah, that's good there. So if the agent is dead, or if all of the agents are dead, better said, we train the network, the long memory of the network, and then we reset the system. Before that happens, we iterate over every agent, and then we applied this algorithm, which is the algorithm that connects with the training of our synthetic brain and using what is known as the Q value function. So first we need to get the state, then we get the action, and then we play the step. So here we are gonna build a couple of helper functions to allow the agent to get informed on how its environment is doing at the time when it has to play that step. So first we begin with the reward. The reward will come first with the interaction of the paddle with the ball. So we're gonna call this self.collision paddle ball, and we're gonna pass this agent. We don't need to pass the list of foods, quote unquote foods, which is in reality the balls, because we are in the game manager, so we have access to it anywhere else. And let's pile them anywhere. We're gonna put it up here. Collision, paddle, ball. We call self, of course, we're still inside of the class, and we are gonna receive an agent. So the general rule is find the closest ball. There is of course many ways to do it, some of which are more complex, but what we're gonna do is to find the closest ball in the case that there is more, who knows. And that closest ball is gonna contain a hitbox. We're gonna ask if the hitbox is touching the hitbox of this agent, and if the answer is yes, then we yield a reward. Okay, so the first thing we're gonna do is to go through every single ball in the list cell.foods. Sorry about the name. I had to generalize in the template for the RLPP. I know not all foods are gonna be foods, but you know, it is what it is. So here we're gonna ask if the ball's hitbox, which is called the rect component, is colliding against the agent. And if the answer is yes, we add to a reward, and we are gonna add 10. We begin with an accumulator called reward 0, and at the end we return it. Once that's done, the information will be given over here. Now, of course, we don't have a reward already here in the update function, so I'm gonna erase that reward plus equal. I'm gonna set it reward equal. We don't have a variable before then. The next one though, we do have. So by the time we write the next one, the next reward, we are actually updating the previous one. So in this case, we need to evaluate the collision of the ball with the blocks. And we are not gonna pass anything. Let's create the helper function up here. So we are still inside of the game manager. So that means we can access the list of foods and the list of walls. At this stage, because we have multiple elements in both ends, potentially, we need to use a for loop to iterate over each of those. So let's start with the walls. For each wall in the list of walls, which are the blocks, we are also going to go through every single ball in the list of foods. And then we need to use the wall and we need to use the ball somehow. So what type of interaction happens between these two? It turns out that the type of interaction is the same as with the interaction with our paddle. However, there is additional steps that have to be involved. In particular, the bouncing behavior. So when the ball hits the block, it can do it from either of 4 different directions. You can hit it from the left wall, from the right wall, from the bottom, or from the top of that particular block. So we need to create a helper function for it to determine the new velocity in the x and the y of the ball. So we're going to call that here, and we're going to call it something like self.update ball velocity, something like this. And we are going to pass 2 elements. We're going to pass the particular ball that is being updated, and we're going to pass also the particular wall that is being hit. This helper function is going to modify the parameter dx and dy of the ball, and it's going to do it by evaluating which of the 4 corners of the wall is the closest to the ball. Let's assume that we have that out of the way. Then we want to work on the wall and the ball interaction, and finally we want to break the code, and this is going to help us because we are supposed to destroy the block, right? So we're going to take the wall, actually the cell.walls list, and we're going to remove this particular wall. The reason why we break the code here is because we don't want to finish the for loops. If the block has been destroyed and there is more than one ball in the game and the ball is trying to access in memory the element that corresponds to that wall that is no longer there, we're going to get an issue. So breaking it allows us to move to the next frame, and 1 frame of difference is not going to make much difference in this case. So we don't need to make anything fancy. So here we're going to make use again of the rect component, collide rect, and we are going to use the ball. There it is, and this is going to return a boolean. So if this situation happens and the ball touches the block, we apply this behavior, and I believe this one should also be in there. We update the ball only once it hits the block. So let's work on the update ball velocity, and we are gonna need to place it somewhere above here. Because it is a method inside of the class game manager, we also need to add self. For now, let's make a pass, and we can add exclamation mark so that we can find it easily later. This is something we need to do. We can also just call it to do. It's what many people do. Okay, so we have the collision with the ball and the blocks, and that should yield a reward as well. So we need to add it over here. Reward equals 0 as the accumulator. And at the end, we need to return it, whatever that value is. So to update it, we are gonna add a plus equal here. And this time we're gonna add 5. You are free to modify to whichever value you think is better as a reward, depending on which you want to give priority to. The hitting of the paddle with the ball or the hitting of the ball with the blocks. And then we return this reward. Let's go back here. And now, instead of reward, we're gonna add a penalty. And we are also gonna add the state is game over. And that is going to be the return of the evaluation of the ball's interaction with the edges of the world. So we're going to evaluate collision, ball, edges. And we're going to add no agent. We don't need the agent. Okay, so let's copy this and let's move it over here. Let's create our method, and this receives self. And the first thing we need to do is to evaluate 4 different cases. So let's work in a cardinal direction, in a clockwise fashion, right, down, left, up, or east, south, west, north. So this is the right direction, down, left, and up. So what does it mean for the ball to hit the right edge of the screen? So it requires to iterate over all of the different foots. So for ball in cell.foots, now we can evaluate it. And notice that the down direction is special. So I'm going to move it to the bottom, right? Because that one carries the game over. And let's begin with the right direction. So if the position of the ball in the x-axis is bigger or equal, and actually, you know what? Let's evaluate the right edge of the ball, because the position of the ball in X is the center of that ball. So let's call it rect.right. And let's ask if the value is bigger or equal than the right edge of the screen. If this topo is confusing, the screen at index 0 means that we are taking the first element of the screen tuple, which contains the dimensions of the screen, which is at this point in this version of the RLPP designer is always going to be 640 by 480. So we're taking the first value 640 here. Let's go back. We know that if we touch the right edge of the screen with the ball, then the ball has to bounce to the opposite direction in the x-axis. So we take the ball's position in the x, and we're going to make it equal to the absolute value of that number, and we're going to turn it into a negative. That's case number 1. Let's copy it, and let's paste it down here to calculate left. Instead of the right edge of the hitbox that defines our ball, we're going to take the left side. Instead of bigger or equal, less or equal, and instead of the screen at index 0 is 0, which is the very first pixel on the left side. In this case, we only need to bounce. We only need to remove the negative symbol to declare that the ball will start bouncing in the positive direction in X, which is towards the right. Then the up direction. The up direction has to do with the top. I believe right, down, left. I guess it's called top. Yes, because the opposite is bottom. So top and bottom is the name. It's just I'm confused about this name being up or top. Let's try with top. And if the value, and if the top edge of the ball's hitbox is less or equal than 0, that's how we know that we bounce on the top edge of the screen. So we modify the dy parameter, and instead of making it negative, we make it positive. Because compared to other video game engines, Pygame is not really a video game engine, but compared to video game engines, the direction in the y-axis is flipped. The screens are actually rendered from top to bottom, and that's how Pygame understands those coordinates. So basically, the bigger the value in y, the more down you go. And we have the last case, and this is the special case because it carries the game over condition. So this should be bigger or equal than the screen at the index 1, right, which is the height, and this should be the bottom. If we're touching the bottom edge of the screen, we are not gonna flip this anymore. This goes away, but rather we're gonna set is game over to true. This is a local variable right here, so we need to create it above, and we're gonna set it equal to false. At the beginning, without any additional evidence, we don't assume anything. So if we finish iterating or over all of the different balls, then we set this game over equal to false. Before we do this, we also need to associate this to a particular penalty. And the penalty will begin at 0. We're not gonna subtract any potential reward right away. And down here, when we know that we lost the game, that's when we add the penalty. And let's set it equal to -10. At this point, it may be interesting to evaluate a different way to express the penalty for losing the game, because not all different scenarios are the same. So if the ball touches the bottom edge of the screen at a distance that is the farthest from the paddle, in this particular scenario, we can imagine the ball being on the rightmost side of the screen and the paddle being on the leftmost side of the screen, then the penalty should be bigger than if the paddle missed the ball just by a couple of pixels. So in that case, we can take the distance between those two elements. To do that, we're gonna need to receive the agent, and we're gonna put it right here. Let's assume that we receive it. We're gonna need to remember to update the call to the collision ball ages method so that it receives that agent in the game manager. But here, we're gonna use it directly by typing if the absolute distance of the agent's position in X minus the ball's position in X, and then we divide it by what we assume is the farthest distance that these two can be from each other. Now that would be simple to represent with the screen at index 0, which is 640, the maximum width of the screen, but technically it's not entirely accurate because the paddle has its coordinate in the x-axis in the center, and the same happens with the ball. So the paddle will never go farther than the left side of the screen or farther than the right side of the screen minus half of its width. So let's suppose here that we have the layout for our game. So the position in the x-axis of our paddle is located in the center of that paddle. Let me make this green so that we can see it a little better. It's right in the center, so that is the position X of the paddle. And then we have the position of the ball, which is, a little easier to bypass because the corners of this ball are closer to the center of the ball. So there is really not much difference in there, but it still exists. So technically, when the paddle is on the right side of the screen, its position in the x-axis is not the last pixel on that screen. It's the last pixel minus half of the width. And if we take it as well on the left side, where the paddle moves all the way on the left side, the same phenomenon occurs. So that means that we need to subtract the width of this paddle. And I'm just gonna mark it with this width right here. Let's suppose that the ball goes to the left side, and in this case, the same applies. The ball will never go over its left edge, so that means that we need to subtract half of the width of the ball to the left and half of the width of the ball to the right. So let's put it in here. Let's suppose that that is the entire width of the ball. So what is left for our range is this section over here. And this section will be equal to the screen at index 0, which is 640, minus the width of the paddle minus the width of the ball. This would be the way to go if we want to represent it as accurately as possible. But first, we're going to use a screen at index 0 just to reduce the number of calculations. We can get back to this one later. Okay, so now we have a penalty and we have a reward. And then we need to think on what to do with the different balls. So when we only have one ball in the system, we could return here. We could say, give me back is game over and the penalty. And the same happens over here. Return is game over and the penalty. But the thing is that if we lose one ball out of many, that's not game over, even for any of the agents in our world. So how can we represent the state of game over only after losing all of the balls in that game? That is a question that we need to address here. Is the penalty going to be associated to one single ball and one only, or will we also consider penalties for balls that we were not looking at? Let's begin first by removing the returning here. We're going to need it later, so I'm just going to put it over here at the same level. Game over is not going to be updated here, but the penalty will remain in there. So the penalty will be equal to the absolute value of the distance between these two. That's going to be scaled from 0 to something close to 1, not exactly 1. And then we're going to need to multiply it. Let's multiply it by 20. So what we say here is to go through all of the different food items and remove these ball elements. We iterate over all of the different cases, and if at the end of this iteration the length of the list foods, which is the container for the balls, is equal to 0, then it is game over. So we ask if the length of cell.foods is less, or well, actually bigger, equal to 0, then we return is game over and penalty. Otherwise, if that's not the case, we return is game over and penalty. For this one, we can set it to true. It's true that the game is over, and in this other case, no, we haven't finished the game yet. Okay, in both cases, however, notice that we are accumulating penalty for each of the balls that we let go. And I believe that's how it should be. So this is game over, turned out to not be necessary because we are addressing the two cases separately. So we can move to the next part. Okay, back in the update method, we have the reward, we have the penalty, and the is game over state. Let's pass them to the action. And if I remember correctly, there was a place where I needed to add an agent. Right here, collision ball agents. So let's copy it. Collision ball edges. And there we go. Okay, play step. So play step, usually VS Code tells me what I need to pass in there. It's not working right now, but let me check it. So there it is. Play step, action, reward is dead, penalty. Action we're already passing, reward is dead, penalty. So the reward is game over, and finally the penalty. All right. Let's see if this program runs at this stage. After doing this, we'll need to work on the state representation of our world. And okay, so we have an issue here. Penalty, missing one required position in play step. We have play step here. What is happening? Are we passing the action? I guess we're not passing the action. This should be new move. I think I erased it because that should be part of the template. I hope I erased it. I'll check the video afterwards. Okay, and we can see the paddle moving around. Of course, you know, the ball is not doing anything. Whoops! The paddle is moving farther than the right side of the screen. Let's fix that. And that should be in play step. Let's check it out. So what did I do here? Oh, okay. So the left side works, but the right side doesn't. And it's because I made a mistake. This should have been right, not left. That was strange. That's definitely a non-desired behavior. Let's see if this time it works. So we have the paddle bouncing against the left edge of the screen. That's correct. And just for now, oh, there it goes. Well, it goes going to the right now. And he's getting stuck on the right side. Okay, that works. So what's next? Then we need to update the position of the ball, and we need to go back to the helper function to evaluate the collision against the blocks for each of the balls. So let's go to the data definition of the food. So data definition food represents our ball in this case. You're free to change this definition to ball if you so desire. I'm just going to keep it like that for simplicity. But what we are going to do is to add a new method that is going to update the position of our ball. And to do that, we're going to update the value in the x and the y. And that's rather simple to do. So we take the value in x of the ball and we add the value in the x. And we just repeat, this time for the parameter y. We go to the game manager, which is down here. And in the update function, before we enter the agents, we can add it here. So for every ball in the list of foods, ball.update position. Let's see if this does what we want. And it does. Okay, incredibly slow, but it seems to be working. And it's going to the downside and the program is repeated. So that is good behavior. Let's modify the velocity in x and y. And in here in the initialization, we're going to set it self.dx equals self.dy equals, and let's use randomization. Let's go to the top of the document first and let's create hyperparameters, constant parameters for our program that we can change later. And this is going to be called ball dx, and this is going to be the maximum velocity in the x-axis. The bigger the value on the positive side, the fastest it goes to the right. The more negative the value is going to go the fastest to the left. So let's set it to, let's say 5. We can then modify the speed. Let's make the speed 8 for the paddle. And the same for the y-axis. And for the y-axis, I'm going to set it to 3 just to give the agent enough time to catch the ball once it sort of like gets a sense of the trajectory. If we make the vertical change fluctuate too fast, then it may be hard for the initial steps of training. And let's use these parameters. So I'm going to copy one of this, and then I'm going to go to the data definition food once more. So here we're going to take random, and we're going to take an integer that is going to go from 0. Actually, it should never be 0. From 1 to maximum ball dx. So it can give us a value from 1 to 5, I believe. And then we can multiply it by a positive or negative value. We can use random choice, and we can pick -1, and we can pick +1. So it's just going to multiply by positive or negative. Let's see what we do with this. So this second element will be equal to max ball dy. That's always going to be the case, and it always begins by going down. We wanted to always give a hint to the paddle by making or forcing the ball to bounce in the initial steps of our game in order to give the agent a sense of reward so that it begins learning what it needs to do. Let's see what happens here. Okay, running the program once more seems to work. And now we need to update the value of the paddle with the ball, because there seems to be a semantic error there. Let's go to the update function once more here. And we have the collision of the ball with the edges, collision of the ball with the blocks, collision of the paddle with the ball. That's the one we want. So if the ball touches the paddle, the reward is plus equal 10, but then also the ball's direction in dy is gonna be always negative. So it's negative value, absolute value of the current value in dy. Okay, that should do it. And you know what? Why don't we ask? Yeah, I guess that's fine. I was thinking on the bottom edge, evaluating the bottom edge of the ball, which would be more physically accurate, but I think this is fine. And there we go. Look at that. Now the ball is bouncing and destroying the blocks wherever it goes without anything stopping it. And it's because, remember, we have a helper function that we need to finish. So let's work on that, and then we can move to the state representation. Okay, so at this point, I'm going to drag you to the book, and we're going to scroll down until we find that particular section of the code. Here it is. Look at that. Update ball position, overlap left, right, up, and bottom. Let's copy it, and then we can discuss the code. So there it is. I take this pass, and then I paste it, making sure I take care of the inconsistency on the tabulations. And then we have the wall. Notice that the code is calling it a block, so let's call it a block 2. So what is this doing? We begin by calculating the distance of the ball center in the X or Y axis, depending on which wall of the block we're looking at, and calculating their distances. Once we calculate the distance of the ball to each of the walls in the block, we keep the minimum distance, and then we go through the 4 different cases. If the minimum distance is the right, then we update the velocity in dx. The same happens to the bottom. Remember, going down means adding pixels. So that's why this absolute value stays as positive. Compare it with up, which adds a negative value. And also with the left direction, right? Modifying the x and dy respectively. Okay, and look at this. There is a typo. I just found a typo. So this should be dy because it's overlapping up. I hope I didn't carry that later in the code, because that could have caused so many problems when I was trying to work with other things in the network. Oh boy, Uriel, keep it together. All right. So once we have this, now we can return it. We can return. No, actually, we don't return anything. Let's bounce the ball and let's see if it works. All right. So at this stage, congratulations, you're still with me. We have created a paddle that is able to move around by listening to what its synthetic brain says, as well as updating a ball that changes its position and follows simplified laws of physics that relate to the bouncing behaviors against the blocks and against the paddles. Something important to notice as well is the fact that we have added rewards and penalties. Let's find those out. Let's see what they are. Let's print them out real quick. And that's going to happen in the play step method, because this is where all of that information kind of like aggregates. Let's put it in here. So let's print, before we add the penalty to the reward, let's print the reward and let's print the penalty. Let's see what they are. So during playtime, as long as the paddle doesn't lose the game, then the penalty should be 0. Let's see if that's the case. And it is. And we have something else. Something else here. Penalties false? Well, that's wrong. That should not be the case. I need to fix that. Let's see what happened here. Okay, action reward is dead penalty. Let's go to the call to play step. Action reward is game over and penalty. Yeah, but that seems right to me. Is dead and penalty. Is game over and penalty. The error may be on how we're passing the information, because I think that is game over comes before penalty in the return of this method. Let's find out. And we return the boolean first, then the penalty value. the boolean first and the penalty value, and that's the error. Yep, because it should be flipped. So this is the penalty value, then the boolean. So we flip it and we run it. That should be it. Let's see what happens. Let's scroll up. Let's find our print again. Where are you? Where are you? Where are you? There you are. Okay, 0, 0, and let's find out. So we're about to touch the block. So that should give us, I think, 5 or 10 of reward. And there it is. So reward is 5. Over here, it's right there. Then the ball keeps going down and eventually it escapes. Notice that at this point, the ball is touching the bottom edge of the screen, so that correlates to a penalty. And that penalty should be almost the maximum because the distance of the paddle with the ball is almost the entire screen. So let's see. And it does. So the penalty is sub 16. At this stage, I should not be adding the penalty. I should be subtracting it like this. So we get negative numbers. Let's see. Okay, so let's see. After adding the penalty to the reward, when losing the game, we should get a negative value. Oh, now you're doing great. The behavior that you see, by the way, is random. At this point, it has no perception of what is good behavior or what is not. Okay, so we touch the bottom, and indeed, look at the reward. It's negative, right? And it matches the value of the penalty. So that is correct. Okay, so let's remove this print. We don't need it anymore. And let's talk about the state representation. So it's probably a good idea to keep the narrative for the state representation of our agent's environment in combination with how to fine-tune the network so that we ensure proper learning in the next video. So I'll see you in the next tutorial. Should be around 20 or 30 minutes more, and we're gonna have our game of Breakout. I'll see you then.